So this presentation is about level-set topology optimization with PDE Generated Conformal Meshes. And the important part here is really, we wanted to develop on this project a topology optimization approach where everything can be done kind of in a finite element framework, like for example, MFEM. So everything is basically PDE-based. So you already heard today and yesterday a few talks about topology optimization, but just to introduce it again and kind of point out what are the normal tools we have and what are the advantages, the drawbacks of these tools, and why did we, kind of work on this development. So I borrowed this picture here from Boyan. This is an A380, and this was kind of, I think, early 2000s, the first time topology optimization really used in the engineering community, or at least got the attention it perhaps deserves, because these engineers thought, hey, can we actually reduce the mass of this airplane by designing certain structures with the help of topology optimization? And the place where they chose to do this is kind of here in these wings. So these ribs, they decided to use topology optimization for this. And at the time, and even nowadays, the most common topology optimization tool was this density-based topology optimization tool. So in this tool, basically, we have these densities, kind of a density of close to 0 means that's a void region, and that's normally white in here, and that beige and black, which is black, is material. And so we normally start with an intermediate design here, an intermediate design density field, and then throughout the optimization process converge towards a black and white design, and that's then our final structure. And at the time, they used this method to get an initial guess kind of for their design, and then they manufacture something which at least closely looks like what they optimized for, and they drill some holes in it, which probably changed the properties quite significantly. But in the end, they wrote a paper and said they were actually able to reduce the weight of the airplane per airplane by 700 kilograms, or what is this, 1,500 pounds. So that's actually not bad. I don't know if a good engineer could have not done the same, but topology optimization kind of here got some attention. Now, what is topology optimization? I just want to lay out basically the workflow one more time. We heard about this earlier. And basically just point out later on where MFEM and all the results basically fit in. So normally we have this initial design. It's a design field. It can be a density-based field, the way basically these Airbus people did it. But it could be something else like a level set field. And this field could be defined through some primitives, which are defined through a few parameters, or it could be discretized over domain. It is a field which basically defines the geometry. Then we calculate normally a response based on this geometry definition. And of course, we need here something to analyze this. It's ideally cool. Something cool is if we have a conformal mesh. That's where we want to go with this word. And then we have some performance measures. We compute these performance measures based on the calculated response, and then compute some sensitivities, where the sensitivities are basically the derivatives of these performance measures with respect to these initial design variables. And then based on these sensitivities, we update the design. We check if the design is converged. If it's not converged, we basically start the whole process over again with the new updated design as our initial design. Our optimization problem normally is a minimization problem. So minimize the objective subject to a constraint, and the objective and the constraint kind of consists of these performance measures, and they could be something like strain energy or mass or some regularization terms. In this work, we, at least in the presentation, the ones we use is mainly the most simple ones: strain energy, some regularization terms, and subject to one or multiple mass constraints, just to show basically how the workflow works. So now in classic topology optimization, I have here 3 different methods what we use. So the most common one is this first one. It's the density-based one, and it normally converges to these black and white designs. The big drawback of this method is normally that in these boundary regions or interface regions between materials, we still, and no matter how sharp you make the function or whatever, you get these intermediate designs. And the question for post-processing is obviously, how do you post-process this to manufacture the stuff? Or what do you do with these intermediate designs if you have physics like contact, where you have, boundary phenomena, or you have boundary layers, whatever. The reason why this method is so popular is really because the moment you have kind of a finite element code, something like MFEM, implementing this method is pretty straightforward. So that's why people like to use it. But it has a drawback. Now there are other methods, like for example, level set methods, where we define the geometry for a level set field, and that's what I will do here. But now the question is, how do we analyze actually our structure or our design? And one method to do this is with body fitted analysis method, analysis meshes. The question is now, how hard is it to actually produce an analysis mesh like this? The more complex the geometry, the more complex it is to produce these meshes. Sometimes we have to use external tools linked against these tools. The last one I want to point out is immersed methods. I think they are great for these applications. The problem is not every finite element code actually has this non-standard finite element implementation where we can solve these immersed problems. And even if we can solve them, they have their own issues, like basis functions with small support, which results in really bad conditioning, and we have to stabilize the stuff. So what we would like to have, and this was the point of this work, we want to have kind of this crisp geometry description, and then ideally a conformal mesh, which is easy to produce. Yes. Okay, with this said, we decided to use this level set based topology optimization approach. And in the level set approach, normally, or in our case, the geometry is implicitly defined by the isocontour of the level set field. And as I already said, in my case here, the design variables are directly used as the coefficients for this level set field discretization, but we could also use, simple structures like a circle, which is defined through a small set of parameters and define the level set field this way. And then, of course, we have now the geometry description, and we compute the sensitivities. We'll talk about this. And then we update the design. Now, we heard yesterday in a talk where by Adrian, where they did similar thing, and they used the Hamilton-Jacobi equation to update the design. We could do this here too. For no particular reason, we decided to use a nonlinear programming technique, the method of moving asymptotes. You heard about it in the last talk, and you got a shout out. I didn't know about this, but we have right now a PR of an MPI capable version of MNA and MFEM, and the moment hopefully makes it like the one can use this MNA to run problems like this one. Okay. So this here is an overview basically of the big picture of this topology optimization approach. So at the top here, we have the level set field defined over design mesh. And you can already see this design mesh is in this case a simple tensor grid with some one elements. Nothing special. This mesh stays constant throughout the optimization process. So the number of optimization variables stay constant, and we basically update in the level set field here, never decided, right? And then we have a second mesh, which is the analysis mesh, and that's a completely different mesh. This mesh can, in theory, change in every design iteration. We could form some AMR here if it's useful. But the idea basically is to start with a mesh which is simple to produce, like this tensor triangular grid, and then morph the mesh to into a conformal mesh. The way we do this is we first kind of assign element classifications to all these elements. So that's just your inside, your outside. There's some smartness involved, and we do this based on the level set field. And then we use here a pure PDE-based conform morphing process to achieve this conformal mesh, and we can now use the conformal mesh to perform the analysis. Now the mesh morphing process is performed with the TMOP, the target matrix optimization paradigm, and this was not developed here in this work. It was developed before, but we decided to utilize it, and there is a mini app in MFEM, the Mesh Optimizer mini app, which does exactly this. So originally TMOP was developed to improve the mesh quality of highly distorted meshes. So that's this first term here, and then we have a second term, which is the interface splitting term. So this term basically aims to conform a set of nodes in this formulation to the isocontour set field. So in the end, it adapts the mesh to conform to this implicit geometry and kind of in a weak way both together restores this element quality. And as you can see here, this works in a really nice way. I'm not presenting you something. Now, before I go into more details about the topology optimization formulation, I thought I'd show one result, which kind of, it's this really simple problem, but it highlights basically this part of the optimization process. So that's the analysis mesh. That's the level set field. In level set topology optimization, it's often the case that we only have design sensitivities or non-zero design sensitivities at the boundary or at a material interface. So we kind of have to start with some form of initial design. So I create a level set field which has these little holes. Over here, you can basically see the mesh. So the whole domain basically has this mesh. And now when we run the optimization problem, the design evolves and we converge basically to an expected classical cantilever beam problem. But the interesting thing is that throughout the optimization process, we have a conformal mesh in every design iteration. And this mesh is produced through a PDE-based mesh morphing approach, which means we don't need any external libraries. And if you look here at the objective and constraint function, we can merge to a some form of minimum while the constraints are satisfied. The mesh quality throughout the optimization process. So I picked here one iteration. It's basically a random iteration and just analyze basically the quality of all these elements in the mesh. So that's the mesh quality over the element index, where the elements order kind of in a order such that the worst quality element is the left. A mesh quality of 1 is basically a perfect element, and a mesh quality of 0, you see it's a logarithmic plot here. Mesh quality of 0 would be an element which is about to invert. And we can see if we do it kind of right and assemble or basically apply some smartness here when we assign these element classifications, then actually we get a pretty good mesh which can be used for the analysis right away. Okay, now I want to talk a little bit more about the optimization problem, because in topology optimization, it's often the case, I mean, there are some things which are pretty straightforward, and then there's a lot of other things going on. And these other things are to just pose basically a well-posed optimization problem. So what's normally standard is that we have some form of filtering of the design field. So that's the top box here. And I will talk on the next slide in detail about these. This here is our mesh morphing process. We have some regularization, which is of the level set field, which is the right arm here. This one here is a detection of disconnected islands. So in level set topology optimization, it can happen that suddenly there's a free-floating island of our structure, and we have to do something with it. Otherwise, obviously, there's some rigid body motion going on, and then we have an analysis. The big takeaway here is that in this kind of optimization graph, all the operations are basically just PDE-based operations, and they are all implemented in one way or another somewhere in MFEM. Okay, the first one, the PDE filter, that's a pretty standard thing. Normally, we use it to increase the convergence of the optimization problem, to create some mesh independence of this design variable field, and in our case, to promote some a smooth filtered level set field. The reason why this is advantageous in this approach is because we obviously need a fine enough analysis mesh to represent all geometric features of our geometry. So if we don't have the resolution in the analysis mesh, I mean, we can't represent something. So if we can kind of control in a weak sense the feature size here and kind of guarantee that the analysis mesh is fine enough. So that's a nice thing. And there is a PDE solver like this somewhere in the mini apps common folder. So it's basically ready to use. The second thing we use is a level set regularization. So in level set topology optimization, I hinted about this. It sometimes happens, for example, and it's only one example, that we have these disconnected islands. The design sensitivities are only at the non-zero at the boundary, so the island will probably disappear, but the moment the level set field basically sinks through the isocontour level, there are no sensitivities anymore, so it will just linger around. And now, when we use an MMA, there are tons of different reasons from round-off errors. It can sometimes happen that these islands, just for one iteration, pop back in, and it really makes the topology optimization problem kind of not as smooth. So regularizing the level set field is always a great thing, and the way we do this is we basically penalize in our optimization formulations the difference between the actual filtered field and a truncated version of this sign distance field, and we compute the sign distance field with this P-Laplacian solver here. It's also in the common folder of the mini apps. And then, then penalize the difference based on but it penalizes the values and the gradients, and there are some parameters we can choose. But it allows us basically to really promote a nicely regularized level set field with gradients of around 1 at the interface, and then level set within the interior values at the upper or lower bound. And that's also a great thing to have this regularized field for the mesh morphing solver. Now the last thing is this basically detection of these islands. So islands in level set topology optimization, I already said it. They're basically free floating. They cause stability issues, so we kind of have to do something with them. And the way we did it here is we solve kind of this temperature, this little diffusion problem with a zero-degree boundary condition here, a high conductivity. And by doing this, all the regions which are basically connected to the structural boundary condition have a temperature close to 0, and all the other ones have a temperature close to 1. And then we can just basically stabilizing him with these springs, or this mass term here, where we originally I plugged basically the temperature through a heavy side, which now really allows to stabilize the islands, while the rest of the domain is unaffected of this term. Now, we heard a few talks this week where people hinted, or yesterday in particular, that in topology optimization we do not only want kind of these optimized for structures with a already manufactured design, but we actually want to go a step further. We actually want to perhaps optimize multiple components. We want to enforce certain geometric feature in certain regions. We want to optimize for not only the structure, but the internal material layout, stuff like this. And in order to do this, we actually said, okay, can we go a step further? Can we optimize for multiple things, perhaps even for an assembly? And the way we chose to do this is with multiple level set fields. So everything what I presented was one level set field, but now just imagine basically that up here, everything up here is, doubled up or tripled, and there are now multiple level set fields going into this mesh morphing solver, and these multiple level set fields basically are there to model multiple components. So the way we did this here is, you can see I have here 3 level set fields. There are now 3 circles. With 3 circles, I'm in theory able to model 2 to the power of 3 number of subphases. So that's the combination of these level set fields. I can compute a unique subphase index for each of these level set fields. So that's just the combination of these level set fields, where this is basically an Heaviside function 0, 1 for each of these level set fields. And then I can expand the original TMOP formulation, the one I presented earlier. So that's the original term for the mesh quality. And this is now a term which is basically a fitting term for every single level set field. And by doing this, we're now able to basically morph the mesh such that it conforms to all of these level set fields. And now, instead of assigning basically just one inside and outside classification to these elements, we assign this subphase index to it, which is basically highlighted here through these colors. In MFEM, that's just an attribute, and so we can now assign material properties to the corresponding elements. Sometimes we, of course, don't want 2 to the power of n subphases, but we want actually less, but we still want this number of elements. And that's why I also have here this customized subphase assignment. So it basically overrides whatever is in here, assigns the elements correspondingly to whatever is in its customized function. And now the only new thing is basically that we don't want to morph the mesh in regions where there is no difference in basically material attribute. So we exclude these nodes from our set here such that the mesh only gets morphed in the regions where we have a difference in material attribute. Okay, with this now in mind, I want to present 2 examples. So most of you saw this one, it seems, this morning. In this example, what we wanted to do is we said it happens very often that we have certain assembly requirements. We say in our structure we want a component which, for example, has a circular shape here and a circular shape up there. Perhaps it has different material properties and so on. And we said, okay, if we have now this multi-material approach, we can model these 2 circular structures, and we can use another structure through a different level set field. We can model them through a separate level set field, and then the middle part of this bracket basically is, in this case, our design level set field. So this is either 3-level set field, one is a design level set field, the other 2 are basically constant, but we could also just allow them to move by defining them through a few, 2, 3 defined parameters. Now if I run this optimization problem, so that's basically how the design evolves. There is some continuation on the maths. This is why it sometimes looks like this little eating art kind of thing. But the interesting thing is really that we're able, throughout the optimization process, to model these 3 different parts of the components, have always a nice conformal mesh for all 3 of these parts. And we can basically enforce these assembly requirements. We can say this has to stay nice and round. What I want to hint here too is that one of the cool things of having multiple level set field is that we're actually able to model sharp corners. So you can see it here or in this 2D example, since the formulation now basically weakly enforces that this node here is assigned to both fields. We can model sharp corners like this and don't lose the resolution there. Okay, now my last problem, that's cantilever beam, the same than the one I showed before, but now we have actually 2 level set fields. And these 2 level set fields describe, so there's the void again, void is white, and then there are 2 different materials. So there's I think the material ratio is 2 to 1. The purple one is a stiffer material, the gray regions are the less stiff material. And now we optimize such that we get a structure basically with an optimized structure with an optimal material layout in this structure. You can basically see how both these level set fields at the same time get optimized to result in a more optimal structure with respect to whatever our objective is. And in this case, I think it's expected that the stiff material is close to the boundaries and where the load is, while the less stiff material kind of fills in the rest of this structure. Now I can go a step further and say, well, what actually happens here if I change basically these material ratios? So this was the one we saw earlier, and then it goes down to a material ratio of 1 to 20. And what we see here is expected that now the stiffer material kind of forms more, and early in the optimization process, this load-bearing structure kind of forms a structure, and the gray material, which is the less stiff one, just fills in a bulky kind of way to provide some additional stiffness here. But the cool thing is really that with this approach and these multiple level set fields, we can do stuff like this. And this is the last example. That's just the same thing in 3D, just to show in 3D we can do the same thing. The orange bubbles there are stiff material, and then we have gray, which is the less stiff one, and we again have this initial seeding. And it's easy to do. It is. Yeah, and basically we get the same design. So the student material is close to the boundary condition, but not environment. The load is in the less different material kind of forms these shear web kind of structures in the middle. So it just shows basically how this whole thing works, and that we're able with this approach to produce basically this conformal mesh in every side here. Okay, with this in mind, I think I'm out of time. So I think the big takeaway here was that everything in this optimization process is basically PDE based. It can all be done with MFEM, and we kind of have this crisp definition of boundaries and interfaces, and we have conformity for the analysis. Yeah, thank you. We use your MFEM for it, and most of the optimization stuff is kind of implemented in this Lido framework, which I think Mike presented yesterday. Right, thanks.